here is a question regarding inelastic collisions and finding the VF of the system. And now we're using an inclined plane just to add a layer of complication, but it's going to be the same old thing. In order to really be able to answer this question, we're going to try to figure out what the final velocity is at the bottom of the inclined plane. If we understand what the final velocity is here, assuming then that this is a friction-free surface, the velocity will stay constant as it collides with object number 2. And then they will go off together into the sunset, 1 and 2 combined. So I've given you the height of the box on the inclined plane, and we can use this information just like we did in the lab to find what the hypotenuse is, right? So we have our opposite side. We're looking for the hypotenuse length, because that length will help us to figure out what the final velocity is. Assuming that the object is initially going 0 meters per second, it's going to accelerate 2 meters per second squared down the ramp because there's going to be no friction. So we're just putting the block on there and then it starts to take off. So we're going to look at sine of this angle to find all the information. So we can say sine theta equals opposite over hypotenuse. So we can say the hypotenuse is equal to opposite over sine 21. So hypotenuse equals, and I'm going to change 51, I don't know if you can see that very clearly, but it's 51 centimeters, which is really 0.51 meters. So we're going to say 0.51 meters divided by sine 21, and that is going to give us the hypotenuse length of 1.42 meters. Then to find, so if we assume that this is 0, we're trying to find this now, because this will lock into place. So object 1, when it gets down here, will be going at that velocity. It's going to then collide with object 2, object 1, and object 2 will go off at the same velocity because it's inelastic. So we can say then that VF squared equals VI squared plus 2AD. We have our acceleration. Now I can make it more complicated by not giving you the acceleration. And then you have to find the F net. You can do that by finding F parallel because there's no friction, so F parallel is your F net. You have your mass, which is 1. That's 1. This is 2. I wrote the masses in there. So you could find the acceleration fairly easily. But I was nice and I gave it to you on this one. So we say VF squared equals 0 plus 2 times 2 meters per second squared times the hypotenuse distance. We're talking about this distance to this distance is our hypotenuse, 1.42 meters. So VF squared is equal to the square root of 4 meters per second squared times 1.42 meters. Meters squared over second squared will become second meters per second. So VF equals 2.38 meters per second. Okay, so that's going to be an important piece of information for this part of the problem, right? So now we have that velocity. So now we can do the rest of our work. Okay, so let's make a little grid for the before and after collision. So I'm going to have 1 and 2. So object 1 is 1 mass, or 1 kilogram. Object 2 is 2 kilograms. Just to try to visualize and get a better sense of our information. So we have our mass, velocity, and momentum, MVP, of each object. And this is before they hit. And we can do the same thing for after they hit. MVP. Okay, you can also use the just we will be using this equation. Basically, you're just saying m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. And that's your law of conservation of momentum. The total momentum before is the same as the total after. So if we have our information, this is 1 kilogram. This is 2.38 meters per second. So this is 2.38 kilograms times meter per second. This is 200. So if we add these up, our total momentum before, right, this is before, is a positive 2.38 kilograms times meter per second. The point of conservation of momentum is to say this number is the same before and after. So we know that this value, whatever it is going to be a total of positive 2.38 kilograms times meter per second. So we have the same mass after. The velocity, actually we could just do these as one thing, because these are going to be the same. I was being robotic, like I tell you not to be. So we have our two masses. We actually just have one velocity and one momentum, and that's going to be our momentum. So the velocity is really what we're looking for, and P we know is because the system is moving together. So to find V, we say V equals P over M. Now this is the total momentum of the system after, and we're also looking then at total mass, and it's the final velocity of that system. So we take our values, positive 2.38 divided by the total of the masses, which is 3, right, because they're moving together, they're joined, kind of like a pulley system in which the two attached masses will affect how the system itself accelerates. If they were detached, then we'd have to work it a different way. But our final velocity here is 0.79 meters per second. And that is the final answer for this particular question, which is, again, looking at an inelastic collision, trying to find the VF of the system, and there it is.